and beyond. Okay, I have a bunch of material, a lot of material here to show, which there's different levels of detail. Can't go through it all in as much detail as I'd like, so I'm going to focus on the high points. The slides will be available from the GTC website afterwards, and if I miss something, you can grab those and get some information there. Some review about the OpenACC timeline. Where we are now is 2015. So our plan is to finish an OpenACC 2.5, and it's called 2.5 instead of 3.0 or 2.1 because it's relatively minor changes, but there were a bunch of minor changes, so we decided to give it that number. And then we're also working on the follow-on to 2.5, which is 3.0, and I'll touch on that at the very end, and we'll see where that goes. There are a bunch of other OpenACC talks. I had some pointers there, but I noticed now that some of these are already done, so I won't go into any of that. I'm going to spend 1 minute here on the architectures that we're targeting, architectures plural. This is more or less the architecture we're targeting today and the one you would see on the show floor. For instance, an x86 processor with a big memory, so everything is high here. That is your high-speed cores over there on your left. And the other side is your highly parallel cores. That's your GPU. You have your high-capacity memory. There's as many tens of gigabytes. And your high bandwidth memory. That's your GDDR, which is significantly smaller. And why is it smaller? Because it's more expensive. And this is where OpenACC was initially implemented, but it wasn't the only thing we designed it for. We designed it to have different types of accelerators. For instance, PGI demonstrated and CAPS delivered OpenACC compilers for the Xeon Phi. PGI never productized that, but it has been done. Or you could say something like a Knight's Landing. Well, OpenACC should support this as well. So it still has many of your same features. You have your highly parallel cores, you have a high bandwidth memory, and you have a high capacity memory. So there's an exposed memory hierarchy that has to be taken care of some way. Also, you can implement this on just a multi-core without the hierarchy of memories. You can implement this on an AMD APU where you have your highly parallel and high-speed cores on the same chip, sharing one memory. In that case, they don't have the high bandwidth memory advantage, but they do have the cache hierarchy and your large memory. So it covers all these different architectures by letting the programmer manage data and manage the compute. So those are the two pieces we're worried about. Okay, all that being said, and in the future, Tesla will have this NVLink, which changes some of the trade-offs when you're moving data between device and host. I think this is be a very exciting time. It's always an exciting time to be in supercomputing because the landscape can change in, well, relatively quick time frame. So here's the topics we're focused on. The first one is where we'll spend most of the time. The last two we'll spend very little time on. There was a presentation earlier today by Guido Eukeland about the profile tool interface and how they're implementing it. And that's, if you missed that, well, okay, I'm not going to talk much about that, but I'll describe it a little bit here. So data clause changes, and some of these I'll spend a little bit of time on, and some of these I won't. These are the 7 or so that I'm highlighting here, present and copy versus copy. So when OpenACC started, we made a mistake. Well, you probably made several mistakes, but this is one that we know how to correct. So we had this is not an introduction to OpenACC. I'm assuming you all have some familiarity, and if you don't, well, you're lost, and I'm not going to help you there. So we have copy clauses, we have present or copy clauses. Why do we want both? And the argument was, you've got data on the host and data on the device, and they correspond to each other, so the runtime has to keep a table to translate between the two. We call that the present table. The present table lookup is likely to be expensive, so we want a way to optimize that case. And when the user says, I know that this is the first time I'm putting data on the device, so I'll use copy, and then you don't need to do a table lookup. Present or copy, you do need to do a table lookup. And it turns out we were wrong both times. The lookup is not expensive, and if you say copy, we still have to do a table lookup to see if it's an error. So we decided, well, that was stupid, so we can fix that. So we're getting rid of present or. Okay, you can still spell it present or, you can still spell it pcopy, but it's just copy. So in 2.5, you just have copy create copy in, copy out. It will always do the table lookup. That's exactly the behavior OpenMP adopted, learning from our mistake, I hope. We're also going to expose reference counting behavior, and the point is there, if you're running on multiple threads in the same GPU, you can have data lifetimes that intersect, that overlap, but aren't properly nested, and you have to define when data actually gets allocated and when it gets copied out and so on. And so the reference counting behavior will define that. We have one significant change. This will actually be a change in behavior. The changes there so far will not change the behavior of any correct programs. This one will. So with the reference counting behavior, if you have an enter data copy in and an exit data copy out, if you copy in enter data 3 times, that will increment the reference count 3 times, and you'll have to exit data 3 times to get it copied out. And it turns out Cray and PGI implemented this different ways in the current 2.0 specification. There was a miscommunication because it was not strictly specified in the spec. It was specified in the minutes of their meetings, but it didn't make it into the specification. So we're going to fix this. We will also have a way for you to say, delete the data, regardless of your reference counts. But we're going to have reference counting behavior as a default for enter and exit data. This was an example that actually came from a customer code. What happens if there are aliases in the data? So in this case, you copy in one array, you copy out the other array. So at the top, you would create both arrays and copy in A. At the bottom, you copy out B and delete both arrays. Well, what if A and B are the same array? Same pointer. What do you do? And the way PGI implemented it was left to right. Oh, A, create it, copy it in. B, it's already there, and unwind it the other way. B, it was present, so do nothing. And A, I just copied it in, so delete it. So the data never comes back. That's probably not what you want. So we're going to define the behavior here basically to do the right thing. If it's on the same directive and there are aliases, it'll do the union of the data motion. Another significant one here is, which matches what Cray does, by the way. So, allocatable arrays. So this is an addition for Fortran allocatable arrays. I know there are masses of Fortran programmers in the audience today. Well, at least 2. And if you have a Fortran allocatable array and you use ACC declare create, this is specifically for global arrays like modules, but it works in other places too. If you have ACC declare create, then it not only creates the space for the descriptor on the device, but the defined behavior will be, if you have an allocate or a deallocate statement, it will allocate and deallocate device and host copies as well. Because that's what you're going to be saying with the declare create. Some other things, update device and update self. If the data is not present today, it's an error. We're going to define that as a no-op. And default present, we're going to have some sort of way to say default present to say, because we had users say, I want to know that all the data is present because I think I'm managing all the data movement. I don't want you to add any data movement. So that's what this default present says. Just assume all the data is present or check that all the data is present, and anything else is an error and I should know about it. And that's all the data stuff. We've had users ask us for directive equivalents of some of the API routines and API equivalents of some of the directives. So as much as possible, we're going to try to keep equivalence between the two. So we have an init routine, they wanted an init directive. We have a set device num routine, they want a set device num directive. We have a way to do a copy in asynchronously or an update asynchronously. Now they want an API routine that does an update asynchronously. We have API routines for copy in and update, but not async versions, so we're going to make those two things equivalent. Some new restrictions. So, okay, so this is one of the big differences between OpenACC and OpenMP. So in OpenMP, you can have an orphan loop in a routine. You can call the routine, and then you go parallel inside the routine. So the routine gets called redundantly by each thread, and then in the thread, you do your work sharing loop. Fine. You can have a reduction on that loop. Fine. And why can you have a reduction on that loop? Because at the end of that loop, there's a barrier. It's defined in the specification. And that's where you accumulate the final reduction? Well, in OpenACC and the gang loops, there are no barriers. And why not? It's a fair question. Because the GPUs don't do barriers across thread blocks. It just doesn't support that. So rather than try to support something that doesn't work, we don't have it in the language. So you can argue that was a good decision or a bad decision, but that is the decision. So because of that, you can't have a reduction in gang loops in an orphan gang loop in a routine. An orphan loop is a loop that's not in a parallel or kernels construct, tightly nested. Okay, so that will be specified in the standard. Reductions, this is a sore point. We're going to, and it's one I don't necessarily agree with, but this is the way it will be in the spec. No reductions on struct members or C++ class members or arrays. And you may ask, why can't I just do this on an array? OpenMP allows me to do this on an array. Well, yeah, OpenMP does this on an array by creating a private copy of the array for each thread. How many copies of that array did you want in OpenACC? How many tens of thousands of copies are you going to create? This is an issue. So we're going to need a way to do a reduction without having to create a private copy for each something. We haven't worked that one out yet. This is another one that I lost this argument, and that's fine. So with ACC routine, you're going to have to specify either gang worker vector or sequential rather than having any one of them be the default. And you can argue that's a good decision or a bad decision. There it is. That's fine. A bunch of minor things. Oh, I'm way ahead of time. I'm going to finish about 15 minutes early. Minor clarifications or changes. Right now you have async, and I didn't actually hear the speakers earlier in this session talk about use of async. Did you use async, Aaron, in your? So he says he did in one of the codes. We had some presentations earlier yesterday, I believe, where they found using asynchronous computation was really important to get all the performance. And with async, you can have a bunch of different queues. You can launch basically kernels and launch data movement on different queues, and so they can potentially overlap with each other, and you hope that they do. But if you're doing this through a call tree, then you have to pass this async ID all the way through. That becomes extra state in your program that you'd like to avoid because it's only for determining which queue. So we're going to allow you to change the default queue, and then you can just put async inside your code, and then you get back up, you change the default queue, and then it will go on a different queue, and change the default queue, it'll all go on a different queue. So that'll be fine. Some other interesting things, the ACC cache. So this is another one where we didn't specify it, and the different compilers implemented this a different way. So if you're not a C programmer, and none of you are, the xi:3 means starting at xi and going for 3 elements. So that would be, in a real language like Fortran, it would be I to I plus 2. I'm not showing my biases here, by the way. What happens if you refer to I plus 3 in the loop, or I minus 1 in the loop? And so right now, for instance, the PGI compiler goes through all these conniption fits to try to figure out, is this reference lying within I to I plus 2? And if not, then I'd better load it from global memory, and on and on and on. So we're just going to define it. If you put cache in there, all your references must lie in that cached space. A little bit of cleanup for private reduction. I don't think that's particularly important because it does exactly what you'd expect. And yeah, big deal. We're using LaTeX instead of Word. That's so we can use Subversion for multi-user, multi-author version control. Now, I don't know which is older, LaTeX or Word. Okay, a little bit on this Profile Tools interface. And so today, this is a tech report, and we're working on editing the tech report, and there's some hope that we can actually get this in the specification. And some depression, we didn't get it in the specification before GCC started their implementation, so they probably don't have this in their implementation that's coming this year, I believe. So the way this works is the profile library will register callbacks with the OpenACC runtime. And so the callbacks will happen synchronously with the host, but asynchronously with the device. You don't get callbacks from the device because that's not always supported. So things like, I'm launching a kernel, I'm starting data movement, I'm entering a region, there's a few others. I'm waiting. That's probably an important one. And then the profile tool or trace tool, what have you, will get these callbacks and then can do other things. It will have information in there like, what's my CUDA context? What's the device I'm using for data movement? Maybe what's the size of the data, or what's the name of the array, or what line in what program did I start from? And it can collect information or even use calls to cupT or whatever other profile interface it may have. So there's some of the events that are there. Most of you don't care. You just want the doggone profiler to work. The point is, with a standardized profile tool interface, then guys who are running things like Vampire or Tau or HPC Toolkit or what have you can write their interface to this, and then that should work across multiple implementations. PGI has implemented most of this already. As the prototype implementation. It'll probably get modified before it gets adopted, but not by very much, I hope. And that was the talk that Guido gave earlier today, I believe. It was a nice talk. Today? Yesterday? Yesterday. And so I really am going to finish quite a bit early. I ran over time when I practiced this, but I don't know why. All right, so they said I ran over, so I had better cut it down. So I did that successfully. So what happens after 2.5? So the signature feature in OpenACC 1.0 was, well, data regions and compute regions. And the signature feature in OpenACC 2.0 was procedure calls, the routine directive, and allowing for procedure calls. And there's a little bit of cleanup in 2.5, fixing mistakes and adding some minor stuff, but nothing significant, as you can imagine. What happens after that? Well, deep copy. And this is a big deal. It's particularly a big deal for the C++ vector class. So the vector class, how's the vector class implemented? You have 3 data members, and they're all pointers. The begin, the end, and the end of where it's been allocated. That's a typical implementation of the vector class. And when I want to copy this class over there, what do I want to copy? Well, I want to copy the class itself, those 3 data members, and the data it points to. But only the data the first one points to. Because the data the second one points to is actually at the end. It's pointing to what is quite possibly a bad spot. It's some unallocated spot off the end of my vector. And the end of the data that's been allocated, well, do I want the end of the data that I'm using or the end of the data that I'm allocated? Well, those are interesting questions, and that's far beyond what a compiler should try to do automatically, right? If I were to see this with 3 pointers in it, and I said, I'm just going to copy this thing automatically, I'd try to figure out where does begin point to and copy all that data, where does end point to, copy all that data. Okay, anyway, so this is new behavior. What you really want to do is have some way to tell the implementation, when you copy this struct, also copy the data between begin and end, fill in begin with the pointer to the begin, fill in end with the pointer to end, fill in data end with, well, I don't know, maybe a copy to the end of data end, but those 2 end pointers point relative to the beginning. It's a challenge. And it's not just this. The other case we have is it was a Fortran, I've forgotten the application, what type of application it is, but they have a Fortran array of derived type, which is basically a struct. And some of the members are allocatable arrays of derived type that have members that are allocatable arrays of derived type. Well, this is a big structure. You copy this whole thing, then you want to copy each one of those submembers, and each one of those will have submembers, and maybe you don't want to copy them all. You just want to copy some of them because you don't want to run out of memory on the device, and on and on. So we're working on, this is a challenge, and it's also an opportunity. So we're working on a way to describe this in such a way that it's rich enough to get the behavior that we want in the cases that are important, but not so complex that nobody can understand it except the guys who designed it. It's a challenge and it's an opportunity. And with machines coming that will have shared memory or unified memory, it's likely to be less important, but it will still be a performance tuning or performance optimization opportunity even in those cases. So we don't think the need goes away. It just becomes not a correctness, it becomes a performance enhancement. So here's our timeline again. I think I already showed this once. Our target is to finish 2.5, to finish all the decisions by May, and then just to finish editing the text in the next month and have it out this summer, and then to keep working on the deep copy and have it out late this year, early next year. I make no promises there, but it's a challenging problem, and there is a tech report about the deep copy available on the OpenACC website. I encourage you to, if you're interested in language design and that whole process of deep copy, look at that and tell us what we're doing wrong. Oops, and that was the end of it. That was my last slide, so I'll go back one. And are there any questions?